To simplify, a neuron is a unit that holds a number. This number is called its activation. Multiple neurons are organized into layers, an input layer, an output layer, and layers in between called hidden layers. Together, these layers form a neural network. An artificial neural network is a statistical model that applies learned patterns from data it was trained on to new data. So how does it work? Each neuron in a layer is connected to all neurons in the next layer, and the strength of its connection is called its weight. During training, these weights are adjusted to identify patterns in the data. The activation of a neuron is determined by the activations of all neurons in the previous layer. This is done by calculating the sum of each activation multiplied by its respective weight. To control when a neuron becomes active, we add an extra value called the bias. The bias shifts the activation function, allowing the neuron to adjust its sensitivity to inputs. For example, a positive bias makes the neuron more likely to activate, while a negative bias makes it less likely to activate. This allows the network to learn more complex patterns. The bias shifts the sum to determine how high it needs to be before the neuron is meaningfully active. The following is defined as the weighted sum. This weighted sum is then typically mapped to a range of 0 to 1 with the sigmoid function, or 0 to positive infinity using a function called ReLU. This is the activation function. The final output of the neuron is the result of applying the activation function to the weighted sum. How do we measure the network's performance? We take the actual output of a neuron and subtract it by the desired output, then square the result. We do this for all neurons in the output layer and sum them up. This value is called the loss. The closer the actual output is to the desired output, the smaller the loss will be. An artificial neural network learns by minimizing its loss, which means adjusting its weights and biases to improve performance. We do this using a method called gradient descent, which helps us find the minimum value of the loss function by adjusting weights and biases based on information from the gradient. Think of gradient descent as trying to find the lowest point in a hilly landscape by taking small steps downhill. As the name implies, following the direction of the gradient's descent. A gradient is a collection of partial derivatives showing how the loss changes with respect to each weight and bias in the network. To calculate this gradient, we move backwards through the network in a process called backpropagation. Backpropagation involves examining each neuron and calculating the gradient. For each neuron, the gradient is defined as the derivative of the cost with respect to the weight. Since this involves composite functions, we use the chain rule to calculate it. The derivative of activation with respect to the weighted sum shows how the neuron's output changes when its input changes. The derivative of the cost with respect to the weighted sum shows how the loss changes when the neuron's weighted sum changes. The derivative of the cost with respect to weights shows how the loss changes when a weight changes. This is crucial for updating weights during training. The derivative of the cost with respect to the bias shows how the loss changes when the bias changes. We use these values to get the full gradients of each weight. The gradient's value tells us two things. The sign, either positive or negative, tells us which way to change the weight to reduce loss. If it's positive, we decrease the weight. If it's negative, we increase it. And the size of the gradient indicates how much that weight affects the loss. A larger magnitude means a bigger effect. We collect this information for every weight and bias to form the complete gradient of the loss function. To update weights and biases, we subtract a small portion of the gradient from them. These processes are repeated many times during the training of the neural network, with each iteration slightly improving the network's performance. Once the training is complete, the neural network becomes a statistical model capable of applying learned patterns to new data.